are you? Thank you.
Thank you. Everybody hear me okay? While we stop talking now. So, today I'm kind of going to give you, have you ever seen that show, Dirty Jobs, on Discovery Channel? Oh yeah, true. It's a great way to start. So, I'm going to kind of give you like a solar system edition of that Dirty Jobs show. Basically what I do is play with dirt all day. It's just that my dirt doesn't come from outside, it comes from space. So Sarah said that I was a grad student. I'm a fifth-year grad student at the Lunar and Planetary Laboratory at U of A. And I'm going to defend my PhD in about 2 weeks. So let's not cheer yet. It's a little premature. We'll see how that goes. So 2 weeks from now, you'll either see me back here drinking happily, or you'll see me back here drinking not happily. So like I said, I spent basically the last 5 years doing my PhD playing with dirt that came from both the moon and asteroids. So I'm going to talk to you a little bit about how we get dirt from other planetary bodies and what I study and why it's important for understanding our solar system. So the first question is, so where does space dirt come from? Most of you, hopefully, are probably familiar with the Apollo missions that NASA ran back in the 60s and 70s. Well, unless you think that we didn't land on the moon, and if you think that, please leave right now and actually never be near me ever. Yeah, okay. Just never bring that up around me. So NASA actually landed 6 missions on the moon. They tried to land 7, but one of them didn't work. I'm sure you've probably seen Apollo 13. You know, they got to the moon, but just wasn't in the cards that time. There was a lot of like long shots of Tom Hanks and Kevin Bacon like, looking longingly down at the surface of the moon. They just never made it down there. So that leaves us, we got Apollo 11, Apollo 12, 13, you know guys, 14, 15, 16, and 17. And you can see they're kind of, the locations that they landed on the moon are shown on that picture there with the red dots. So when you think about it, if you look at those dots, there's some dots in like the light areas of the moon, and then some dots in the dark areas of the moon. So it was important that we got soils from kind of both different main types of material that we see on the moon. We don't really need to know what they are other than their light and dark dots, because that's pretty much all that the astronauts knew when they went to the moon. They knew that they should probably pick up some dirt, but instead of sending an actual geologist to the moon, NASA decided to send pilots and military people, and so they got there and were basically like, okay, this looks like a nice rock, we'll pick this one up. Until the Apollo 17 mission, the last one that they sent, they actually did have one geologist on there, and then they very quickly discontinued the Apollo program. So I guess in 1972, people were like, oh, the moon is passé, we're kind of done with that. So that's how we got the samples from the moon. There was also a Russian, an unmanned spacecraft that went and picked samples up, but we're just not going to count this one. So this brings me to my first trivia question. So I don't know what Sarah said, but there's 2 trivia questions in my talk. Do not answer until I finish reading the question, and you will win fabulous prizes if you get it right. So, see what you all think. How many pounds, or kilograms, because I'm from Canada and I absolutely produce anything pounds, of lunar samples were brought back from the moon by NASA? Answer A, less than 50 pounds. Between 50 pounds and 150 pounds for B. 150 pounds to 300 pounds for C. Or some number larger than 300 pounds. Okay, count 3, hands up, 1, 2, 3. Both of you are wrong.
It's always C.
B is also wrong. Wow. So they actually brought back 842 pounds of lunar rocks and soil. That's a lot. all of humanity. So how much space dirt do I actually have from the moon? I've got 5 different samples, or samples from 5 of the Apollo missions, and I have 6 different samples. So 2 samples I have from the Apollo 12 mission. And I basically study the soil material, like Sarah was saying, which is grains that are under 1 millimeter in size. And the way that you get lunar soil is very tedious. You have to write a proposal to NASA saying why you want the soil, what you're going to do with it, why your study is going to be important. That proposal gets sent out to a committee, the committee reviews it, they decide whether you're full of crap or whether it's actually kind of interesting, and then they'll decide, you propose for an amount that you want to take, and they'll decide whether you're actually going to get it or not. And the time between the proposal that you write and the actual allocation is usually a few months, so it's actually pretty efficient. So I wrote proposals for all 6 of these samples from the 5 different missions, and you can see I have samples from all of the missions except for the Apollo 11 mission. I have worked on Apollo 11 before, but just not for this project. So this is actually, in the bottom right corner, there's a picture of them bringing back the lunar samples from the Apollo 11 mission to where their curation facility is, which is at Johnson Space Center in Houston. So you think about astronauts, and you know they have to Houston, whatever problem. So that is more than just a human spaceflight center. It's actually where the curation center is for all of the lunar centers. And you can see inside on the left there the lunar curation facility inside NASA JSC, and that was built and designed back in preparation for the missions in the 60s. So it's been a little bit upgraded since then, but not by much. And so I'm studying the soil, which is basically just the material that's breaking down from the rocks on the surface of the moon. So for each of those soil samples, I was allocated 0.1 grams, which doesn't seem like a lot. For each sample, it's about the mass of 5 ladybugs, so not a lot. But honestly, I could probably keep these samples and do research on them for the rest of my career, and I would never run out. That's how good scientists have become and they can do with very, very little. The soils that I have to be stored securely at U of A. They have to be kept in a safe. I would have loved to have brought some here tonight, but I probably would have been deported back to Canada if I had done that. I left them there. And only myself and my advisor have a combination to the safe, and in fact, not even the security guard on campus who has a master key can get into the room where the safe is located because they have to be that protected. So this is a picture on the bottom right of the actual Apollo 12 lunar soil, one of the samples I have. That is my hand holding it. They come in basically just like glorified mason jars. They're not very high tech or anything. It's just like, you know, stainless steel canister, and then there's dirt in it, and you open it and you say, oh, what is it? And this picture on the left is Alan Bean, who was an astronaut on the Apollo 12 mission. And you know, you see pictures like this, but in this picture, he's actually picking up my sample, which is kind of amazing when you think about it. Here's this guy, went all the way to the moon, brought back a bunch of dust, and now I have a career. My father always says, I can't believe they paid me to do this. So I'm just going to take a brief aside for 2 really ridiculous stories about New York. And I'm going to talk to you about what I do in here. But the first one is that if you think that the United States government is bureaucratic now, you should think about what it was like in the 60s. Because when the Apollo 11 mission came back, and we see this picture on the right here, they actually made the astronauts fill out a customs declaration form saying that they were bringing lunar soils back from the moon. If you look really closely, the point of origin, the circle right there, says the moon. Neil Armstrong's signature is on it, Buzz Aldrin's signature is on it, Michael Collins' signature is on it, and like they were like, you know what, just to be safe, we better fill this out. So that's ridiculous. That circulates the NASA email listserv like every year around the time that they brought it back, because it's just so absurd. The other ridiculous story about, this also speaks to why I have to keep my samples in a safe behind a locked door that no one knows where it is. Because back in the early 2000s, there were some very, very naughty interns at the NASA Johnson Space Center who decided that they were going to get really rich. And they stole a safe that had had lunar soil samples, Martian meteorites, and a bunch of other stuff from this guy I know, Edward Gibson, his lab. And they tried to sell it on eBay. which did not work out well for them. The FBI found out, actually through this guy in Antwerp. It's a very convoluted story. If you're interested in it, you should read this book called Sex on the Moon, which kind of follows the guy that did this. And he's now out of jail, but he was in jail for about 10 years. And so the FBI, in order to figure out, when they were building the case against this guy, what the value of these materials was, they determined that lunar soils are worth between $1,000 to $5,000 a gram, which is a lot. And if you think about that 842 pounds of rocks that we brought back, I think it's somewhere like $4 billion that the lunar soil samples are worth, the lunar soil and rocks are worth. So that's just interesting for you. Don't try and steal from the U.S. government. It doesn't go well. Okay, so that's enough about the moon. Those are some of the samples I work on. The other ones, which you probably are much less familiar with, are from a near-Earth asteroid called Itokawa. And there's a picture of Itokawa right there. It's very small. It's only about 500 meters in length. I actually have a shape model that I'm going to pass around that you can look at. So that shape model is basically exactly what the asteroid looked like, floating out there in space. And NASA did not run this mission to Itokawa. It was run by JAXA, which is the Japanese Aerospace Exploration Agency, so that's probably why you may not have heard about it. It got launched in 2003, and the goal was to kind of study this asteroid and then to also bring back some dirt from the surface of it. It was very, very dramatic, and they actually made a movie about it in Japan, which you could probably find with English subtitles if you want. I watched the trailer, and it was very intriguing, although I couldn't understand anything that was going on. And there was a lot of things that went wrong with this mission. I'm going to try to give you a brief rundown, and you can tell me whether you think it's actually kind of a miracle that this thing actually did anything at all. So 2 of the reaction wheels on the spacecraft failed, which are basically the things that control where the spacecraft is pointing. They had to use their ion engines in order to control any sort of movement for the spacecraft. They had a lander that they were supposed to deploy down to the surface, and that just never arrived. We actually have no idea where it went. It just kind of floated off into space indefinitely. No idea. They did one attempt to collect a sample. The first attempt, they totally lost contact with the spacecraft. They had no idea what happened. They don't know if it touched it. They don't know if it smashed into it. They have no concept. So then they decided, let's go for broke. Let's try a second landing. They did that, and basically it was like an arm that was going to reach out and touch the surface and grab some sample and bring it back in. And the actual mechanism that was supposed to do the grabbing, that didn't really work in the second attempt either. And then they promptly lost total contact with the spacecraft for 3 months. They had no idea where it was. They probably thought it went to safe mode and kind of went a few hundred kilometers away from the asteroid, but they were not sure. And basically, the people at JAXA were working around the clock to try and figure out what happened to it. Then, by some grace of God, they got contact back with it, and they discovered that 2 out of its 4 engines were broken, and that 4 out of its 11 batteries had completely failed. So you're thinking, this can't possibly have been a success. How could they have done anything with this? Well, Japanese are very innovative, and somehow they successfully sealed and launched a sample return capsule, even though they had no idea for both of those supposed touchdowns whether they actually got anything. They're like, let's just try. So here are the 2 potential landing sites, and they have question marks because I think the Japanese are really just guessing at this point. They're like, yes, it probably landed here. And there's no one to tell them that they're wrong. So if you look in the bottom right-hand corner there's a selfie that the spacecraft took as it was descending down. And so they're like, oh, this is great, like we see a spacecraft, and then they have no idea what happened after that. So then there's an artist's conception of the spacecraft picking up some sample. And it made it back to Earth, and it didn't crash into the desert in the middle of Australia. The parachute successfully deployed, and so they had a sample return capsule. And that brings us to trivia question number 2. How many pounds do you think of asteroidal sample was actually brought back by this mission to Ikawa? So A, less than 5 ounces, B, less than 1 pound, C, less than 10 pounds, or D, between 10 and 50 pounds.
Hey!
A is correct. So they actually brought back 1,000 dust particles. This is a picture of the actual sample catcher when they brought it back. Okay, you're all sad. Don't be sad. We can do a lot with 1,000 dust particles. You can actually see kind of in the, down in the well there in the upper right corner, you can see like some specks of dirt. That's good. Considering they thought they had no idea what they were going to get anything back, this is great news. So, yes, how much did we get? We did not get a lot. 1,000 dust particles. Most of those are less than 100 microns in size. So for reference, a human hair is about 100 microns in diameter. So most of the particles they brought back are smaller than the width of a human hair. That takes some very skilled people in order to actually extract and find those samples. So in the picture here, you see circled in a red, in this red circle there, there's kind of like a shadow. So that's a grain that they found. And that long shadow with the diameter about 1 millimeter, that's a glass needle, and that's what they use to kind of pick up. They just use static attraction between the needle and the particle, and it will jump out through them. And then they can prepare it for analysis. So the curation team was very, very careful, and the fact that they got 1,000 particles at all is kind of amazing. And like I said, scientists can do a lot with very, very, very little. So how much space dirt do I have from that mission? Well, I have 3 dust particles. They're all under 100 microns in size. Most of them are about 40 or 50 microns, so half the width of a human hair. And 2 of them came from NASA. So NASA was a partner on the mission. They didn't end up contributing anything to it, but because they were supposed to contribute a lander, and then they're like, Congress was like, you know what? I think we're going to not do that. So, but they still, I don't know, probably paid for part of the rocket or something like that. So they got a proportion of the sample return. So that's how this works with international missions. If you contribute money, you get some of the sample back. So NASA has 20 grains out of 1,000, and I got 2 of them, so that's pretty good. And I got 1 from JAXA. So I have 3 total particles. These are the kind of particles that you don't want to sneeze when you're working with them. And they've made, of 1,000 of those, they've made about 500 of the grains available, which is actually a lot. So 50% of the total sample return to be made available within like the first 5 years is an extraordinarily large amount. NASA, for the lunar missions, I think it's something like over 80% of those samples have never even been touched. Most of them are sitting not in the lunar curation facility, but in like a bunker at White Sands, I think, in New Mexico, because they don't want to have all of the lunar samples in one place in case there's some sort of like terrorist attack, or the thing at JSC gets hit by another hurricane or something like that. So the fact that they've made half of the samples available through JAXA is something much different than NASA. And I have those 3 particles, which is basically like 1% of the entire population of space dirt from Ikawa on the entire face of the Earth. Which is kind of cool when you think about it. Why did they trust me with it? I'm not sure. So what do I actually do with the space dirt? Now you know where the space dirt came from. So what I'm really interested in for my PhD is finding out what's happening to grains on the surface of something called an airless body. So an airless body is something like the moon or a near-Earth asteroid that doesn't have an atmosphere. Earth has an atmosphere, it protects us from all kinds of crap you don't even want to think about. But things on the moon or on Ikawa, they don't have that protection. So they're exposed to this interplanetary space. And that exposure, it can change the grains. It changes the shape of the grains, it changes their chemistry, it changes their microstructure. And that's really important because a lot of the information that we get about these planetary bodies are from remote sensing spacecraft that kind of orbit around them. They're looking for the spectral properties, the optical properties of the material, and that helps you figure out what the sample is made of. But with these processes going on, they change those optical properties of the material. So if we don't understand how they're changing them, we're really not going to get any reliable information about the composition of the material from these spacecraft. So this process is called space weathering. And there's kind of two major things that are driving space weathering that on airless bodies. One is micrometeorite impacts. These kind of just like dust-sized particles are constantly bombarding the surface, and they're melting things, they're vaporizing things, there's recondensation in specific phases, but there's no oxygen, so it's really weird chemistry. And the other one is radiation processes. So there's the solar wind that's coming out from the sun at all times, and it's got hydrogen and helium, and that's irradiating the surface material. And that can cause things like amorphization, which is a breakdown of crystal structure in the minerals. Or you can get the deposition of that hydrogen and helium implantation into the sample. You get sputtering of atoms off the surface. And all of these things, they don't operate on very large scales. It all happens really in the outer 100 nanometers, which nanometers 10 to the minus 9 meters. So it's very, very small. But they have huge effects on the optical properties of that material. So I want to figure out what those effects are. And the way that you study dust particles from another planet is you use a very, very fancy, very, very expensive microscope called a transmission electron microscope. And you probably have in your mind an image of a microscope, and you the train. The train is coming. Except instead of light, it uses a beam of electrons. And you can use the microscope to kind of look at the chemical composition, the structures, the crystal structure of the material. But in order to do that, the sample has to be electron transparent. It's a transmission electron microscope that transmits the electrons to the sample. So in order for you to get samples that are electron transparent, they have to be less than 100 nanometers thick. My samples are, less than 100 microns, but that's like 3 orders of magnitude larger. So what I need to do is take that tiny particle, move it very, very carefully, and use a diamond knife to slice like a loaf of bread, slice off sections of the sample, and then put them into the microscope. So that's what I spend a lot of tedious time doing. So we're talking about space weathering and all these changes that happen, but what do those changes actually look like? So like I said, they're very, very small. The first and probably most important one is something called nanophase iron particles. So they're very, very tiny particles of iron, usually metallic iron, locally produced iron, that form either on the surfaces of the grain, so you can see the black spots. This is like a cross-section of the grain, and those black spots are right on the outer rim. Or they form as kind of larger ones in the grain interior. If you look at the picture on the bottom right, all of those bright white spots, those are bright nanophase iron particles. There's also other things like I talked about, breakdown of crystal structure, melt deposits on the grain exterior, so you get bubbles. You can see the bubbles kind of in the interior of that grain on the top right. But the nanophase iron particles are really important because that's what's really changing the optical properties. So if you don't believe that something a couple nanometers in size can have a significant effect, if you look at that chart, you can see that one of those lines is really wiggly, and one of those lines is not so wiggly. Well, those wiggles are basically what tell us the composition of the material. And the wiggly line is from a rock that we took from the moon, and we crushed it up, and we looked at this light reflecting spectrum from it. And it has wiggles because the interior of that rock has never been exposed to these processes. Well, if you take a soil of the exact same composition, and you look at the reflectance properties of that, you get that straight line. There's no wiggles that can tell us anything about it from remote sensing because it's been exposed to all these processes. So these tiny, tiny little nanoparticles have a really significant effect on what we can tell those composition materials. So we see nanoparticles on the moon in Itokawa, and this was the fact that we had samples from the surface of another planetary body. This is the first time that this had happened in 40 years since the Apollo missions came back. This is the first opportunity to really compare space weathering on 2 different planetary bodies. And we found nanoparticles, these iron nanoparticles, in both. But on the moon, you get a lot of different sizes of nanophase iron. Some of them are large, they're up to 100 nanometers in size. But in Itokawa, you don't really see any big ones, you only see small ones. And we wondered why. Is it because are they forming differently? How do these things form? What do we know about them? So that's where my work kind of comes wanted to simulate the conditions that are happening on the surface of the moon or on the surface of Apollo, but I wanted to do it in the lab and I wanted to watch it. I wanted to do it with lunar soil. So I used one of the lunar soil samples from the Apollo 17 mission, and they put it in this really fancy specialized holder, which basically allows you to heat the sample up to 1,000 degrees Celsius, so like the temperature that an impact event would bring, and back down to room temperature in much less than 1 second. So it's basically simulating an impact event. And I've got a little diagram here about what we think is happening to form these iron nanoparticles. You've got hydrogen and helium that are being implanted, remember, from the solar wind. So they're just kind of chilling in the outer layer. They're just like, hey, we're just hanging out. And then you get some micrometeorite that comes in and impacts. It creates all this heat, it melts, it vaporizes things, it really mobilizes that hydrogen and helium that's just been like chilling there. And that hydrogen can act as a reducing agent for the iron that's in the crystal structure. So lots of minerals on the surface of the Earth have iron in them, and a lot of them are in oxidized form. But that hydrogen is going to reduce the iron, and you're going to get metal. You're going to get iron metal, and it's going to form into these tiny little spheres because they're thermodynamically stable. So I wanted to watch this happening. Like, no one has ever watched it happening. They thought this is probably what's going to happen, but we've never had the technology in order to witness it. So here's one of the lunar soil grains from that mission. This is what it looked like before I blasted it. And it's kind of like flat, looks platy. You don't see any of those really bright spots, in that middle image. It kind of just looks like one uniform color. So let's cook it. So I got a video here that shows you. So both of the panels are showing the same grain. It's just one of them is the surface. The one on the left you're looking at the grain surface, and the one on the right you're actually looking through the entire grain. So in a minute it's going to move, and that's when we actually do the heating event, and you will see what happens to it. It should be fairly obvious to your eye. So we see that basically you get all these spots, and the morphology of the grain is changing. It's much more rounded, it looks more glassy. And so I call this a case of space freckles. Basically, we're creating those nanoparticles that I'm talking about. This is the first real confirmation that we actually witnessed a simulated space weathering event in the lab, and we saw it do exactly what we thought it was going to do, which is very reassuring. And this is a picture of, on the left, that's the surface of the grain after we did the heating event. And then down in the bottom right-hand corner, that's what a lunar soil grain that's just natural looks like. So we did pretty well replicating, you got these big spots on the surface, those are the nanoparticles, there's lots of different sizes, and so we were pretty confident that this is accurately mimicking that process. But we got to make sure that they're actually made of iron, because if you don't check these things, you never really know. So we did some chemical mapping. You can do that inside the transmission electron microscope too, and basically the bottom panels are just kind of like, it's a map. It's showing you an elemental distribution across the sample of what there is. And you can see plain as day that all of these spots are composed of iron, and that there's no difference in the oxygen signature. And that you've got all these tiny little iron space particles. So then we thought, okay, well that was fun, but let's blast it again. Because a lot of grains on the surface of the moon, they're not just going to see one micrometeorite impact in their lifetime. They're going to see a lot, right? So let's just keep hitting it, let's keep whacking it. So we did repeated heating events. For this grain, we did 8 in total. It's the same thing. You're going to see it go pop a bunch of times. And then we thought we should probably have scientific motivation for why we want to do this experiment. So we thought, okay, well, we should look at how the population of nanoparticles changes with each repeated heating event. Do they get larger? Do we get just more nanoparticles? What's the size distribution look like? And if we know that, we have very good measurements of the impact rate on things like the moon, because we've got spacecraft out there all the time that are measuring dust impacts on their surfaces. So we know how often a micrometeorite is going to impact an area of the moon statistically. And so if we equate one of these impact events to a time scale that has likely been on the surface of the moon, and we look at the change in the size distribution of those nanoparticles, this can provide a really rough measure of dating particles, dating lunar soil particles, without having to do any fancy isotopes or anything like that. It's just a relative way. And so yeah, now we're zooming in on it, and we're like, oh. So it's good for us. And so this is what it looked like on the left. That's before. In the middle is after one heating event, and then after 8 heating events is on the right. And after 8 heating events, they're still composed of iron. But you can see they got bigger. There's weird like hitting around the surface, on the surface around those nanoparticles. And so then I did some very tedious counting of nanoparticles, which is not my favorite thing, and I wish I had had an undergrad. And you can look at, on the left, we did 2 different gradients, and you can see that just the size distribution of the nanoparticles is very asymmetrical. Most of them are very, very small. And in the upper right, the size distribution is changing after 8 shocks, which is like an order of magnitude longer sitting on the lunar surface. And it's becoming more normal. It's, it's like kind of evening out. And then after 12 shocks, which is even longer, it's moving even more towards the right. So if we do like steps, independent steps of enough different shocks, then you can kind of compare in a natural lunar soil grain that hasn't been experimented with, how it compares to the experimental samples and get a relative age date for it. So this is a totally new technique that we developed this experiment. So that's just some of the space dirt stuff that I've been doing. But the future of space dirt is very bright. And the reason for that, especially in Tucson, is because there's a mission that's being run out of the University of Arizona called the OSIRIS-REx mission. Hands up if you've heard of the OSIRIS-REx mission. Good job. Everyone should hear about it. Probably some of you work on it. But it's a sample return mission to another New York asteroid. A different type of asteroid is going to have organics and stuff on it, which is a whole other can of worms. But it's going to bring back, theoretically, a minimum of 60 grams of material, which is a lot more than the 1,000 particles that the Jackson mission got. And then I feel like Jackson was kind of feeling a little left out, because they're like, hey, our mission was good too, so we should do another one. So they're running the very imaginatively named Hydrosa-2 mission, and they're also going to a near-Earth asteroid, and it's also a carbonaceous asteroid. So while that's not being run by the University of Arizona, a lot of the people at the University of Arizona are actually working on the mission. They're kind of working in tandem because they thought, why compete? Science is better when we're collaborative. So they have a lot of cross-pollination between their team members. And so, if God willing, I graduate in 2 weeks. I will be spending the next 3 years with my postdoc at Johnson Space Center in Houston, and I'm going to be working on preparing for the sample return from that OSIRIS-REx mission. So looking at how space weathering is going to operate on that planetary body. So that's what I have to tell you about space dirt today. I hope you enjoy it. Anybody want to buy me a beer?
After you.
Any questions for Michelle?